Hello everyone, welcome back to my channel. Today I'm going to talk to you about distributed forces in statics. This is a topic in statics. I'm going to talk about centers of gravity and centroids. And at the end, I'll provide you with some problems and some solutions. I'll walk you guys through the solutions. So here on the top right hand corner, we can see the center of gravity of a flat plate for the x and the y coordinate. We can see the centroid of an area A calculated in this way. Notice that the only difference between calculating a centroid and a center of gravity is that we use the differential element of area for calculating centroid, and we use the differential element of weight while calculating the center of gravity of a flat plate. Objectives. We want to describe the centers of gravity of two-dimensional bodies, and then we want to define the centroids of areas by summation methods and integration. We introduce two concepts closely associated with determining the center of gravity of a plate or a wire. So the first moment of an area or a line with respect to a given axis. It's very important. We calculate the coordinates of a centroid or the center of gravity from summing the moments. We also want to know the centroid of an area or a line and what a centroid means. So computing the area of a surface of revolution or the volume of a body of revolution is directly related to determining the centroid of the line or area used to generate that surface or body of revolution, according to the theorems of Pappas-Godinus. Some planar centers of gravity. This is the first part. We're going to be talking about planar centers of gravity, and then we will move on to talking about centroids. So the center of gravity of a two-dimensional body. First, we want to divide a plate into n small elements. We denote the coordinates of the first element by x1 and y1, and then we denote the coordinates of the second element by x2 and y2, etc. The forces exerted by the Earth on the elements of the plate are denoted respectively by the changes in weight 1, weight 2, and all the way to weight n. Center of gravity of a two-dimensional body. So here we see how we calculate this. I walked you guys through the process just now. A single element of the plate. First, we apply the weight force there. Each element on the plate exerts a specific weight, and then we have multiple elements of the plate that each exert a small weight, and then each of those small weights can be summed up to the center of gravity. Basically a point where kind of we can concentrate the weight. And in algebraic form, I just showed you a geometric interpretation, but in algebraic form, it's the sum of the forces up with respect to z. Because it's pointing down, weight forces always point down. We have the change in weight 1 plus weight 2 all the way to weight n. In integral form, we can think of these changes in weight as very small differential changes in weight, and thus we can use integration now with a differential element of w, differential element dw. And then this is how we calculate the coordinates of the center of gravity. So the x coordinate would be the integral of x dw over the total weight of the object. And similarly, we can find y bar, the y coordinate of the center of gravity, in a similar way. To obtain the coordinates x bar and y bar of the point G where the resultant W should be applied, we note that the moments of W about the y and x axis are equal to the sum of the corresponding moment of the elemental weights. As such, and then afterwards, I showed you guys how to obtain the x bar and y bar. So basically, the first two over here are just simply we obtain the second equation by dividing the first equation by its total weights. So the weight center of gravity of a flat plate, this is a summary of all the equations you guys will have to know. It is sufficient to know only the top or bottom equations, because we can simply derive each of them from the other. Now we're going to talk about planar centers of centroids. the centroid of an area A can be expressed as, for the x-coordinate, x bar times A is equal to the integral of x dA, or solving for x bar and y bar, we obtain this. How do we get this? In the case of a flat homogeneous plate of uniform thickness, we can express the magnitude change in W, the change in the weight force of the weight of an element of the plate, as change in W is equal to gamma times T times change in area. The gamma refers to the specific weight, which is the weight per unit volume of the material. The T refers to the thickness of the plate. The change in A refers to the area of the element. Similarly, we can express the magnitude W of the weight of the entire plate as W is equal to gamma times T times A. Here is a geometric process. So first we divide the area into elements. We can have element change in area at a point X and Y. And then the centroid is then located at the sum of the X times the differential element of the area over the total area of the plate. Centroids are uniform thickness. They are uniform. Okay, so they have uniform density, and that is very important because if they have uniform density, like we can simply use their area, but if they don't, we cannot, because we have to take into account the varying densities across the surface. The centroid of an area is the point where a homogeneous plate of uniform thickness would balance. This uniform thickness is very important. Uniform thickness refers to uniform density. So the centroid of an area A, in summary, these two equations are what it is necessary to know. As previously shown, similarly with the center of mass or center of gravity, you only need to know one of these equations in order to know the other one. These equations define the coordinates and these equations define the coordinates x bar and y bar of the center of gravity of a homogeneous plate. The point whose coordinates are x bar and y bar is also known as the centroid C of the area A of the plate. If the plate is not homogeneous, you cannot use these equations to determine the center of gravity of the plate. They still define, however, the centroid of the area. So centroid of the area, we can separate this concept from the center of gravity. But the thing is, in a plate of uniform density, the centroid corresponds also to the center of gravity coordinates. Composite plates and wires. So basically, so over here we have a few commonly used shapes, except these are for composite planes. You can use these for composite planes, but it's a helpful diagram because sometimes it's very hard to integrate all the time. For a right triangle, for instance, the x bar coordinate is found at b minus b over 3, and then the y coordinate is found at h over 3. Of course, you're going to have to manipulate this according to the specific problems, because sometimes the orientation of the triangle may be different. Here are some more tables. In many instances, we can divide a flat plate into rectangles, triangles, or other common shapes shown in the figure. So this is the figure I'm referring to, these three figures. Familiar yourself with them. We can determine the abscissa x bar of the plate center of gravity G from the abscissas x1 bar, x2 bar, all the way to xn bar of the centers of gravity of the various parts. To do this, we equate the moment of the weight of the whole plate about the y-axis to the sum of the moments of the weights of the various parts about the same axis. We can obtain the ordinate y bar of the center of gravity of the plate in a similar way by equating moments about the x-axis. Mathematically, we have this. So the sum of the moments about the y-axis, why did they use x bar? Well, they used the x bar because when we are summing the moments about the y-axis, the distance we use is actually dx. And that actually makes a lot of sense if we go back over here, because well, we can think of moments also in terms of torque. So basically, when you turn this plate around the y-axis, you kind of want to have this distance over here, because this differential element, you're rotating it about this way, about the y-axis, but the horizontal distance to that point is x. Similarly, when we're rotating something about the x-axis, we're taking the y distance, so we're going to use y in that case. So back to the slide we were talking about previously. Always remember thus that we use x bar with the sum of the moments about the y-axis, and y bar with the sum of the moments about the x-axis. Okay. So basically, here's how we apply the tables we saw previously, these tables over here. When we're given a shape like this, we can sometimes divide it into shapes that for which we know the centers of gravity or the centroids from those three tables that I just showed you. And then we can sum up the moments as such, and we will work through an example problem to help you guys familiar yourselves with that. Hello guys, in this part we are going to talk about problem involving centroids of composite planes, and we're going to work through an example problem together. So this is the problem. Locate the centroid of the plane area shown. The solution is as follows. First, we can divide the shape into a rectangle and two triangles as such. Secondly, we draw the approximate centroids of each shape. For the rectangle, it's approximately in the center. For the triangles, it's approximately there. For the other triangle, it's approximately there. Calculate the x and y coordinates of the centroid of each shape. For the rectangle, we have that the distance over here is equal to 18 plus 24 divided by 2 minus 18. So that is the distance from the origin, remember. X is positive 3 millimeters to the right of the origin. For the y coordinate, from the 0y origin, the distance is 12 millimeters plus 32 divided by 2, which is 28 millimeters. For the left triangle, we can use this triangle diagram to help us out a little bit that we got from this diagram over here. Remember our special shapes and the given centroids they give us. So knowing that, for the left triangle, the distance from the origin of the first triangle is negative 6 millimeters and negative 18 over 3. And then for the y coordinate, it is 12 minus 12 over 3, which is equal to 8 millimeters. For the right triangle over here, that distance is equal to 24 divided by 3, which is 8 millimeters. For that distance over here, the vertical distance, that distance is equal to 12 minus 12 over 3, which is equal to 8 millimeters. So basically, now, this was our solution. So now we can plug in all the given values. The sum of the moments about y is equal to the x coordinate of the centroid times all the sum of the areas. So for example, the 32 times 18 plus 24, that's the area of the rectangle. The 12 times 18 divided by 2, that's the area of the left triangle. The 12 times 24 divided by 2, that is the area of the right triangle. So next up, this is in turn equal to the sum of the centroids of each of those three shapes times the area of the shape itself. So first, the x coordinate of the centroid of the rectangle, which is 3 millimeters from the origin, times the area of the rectangle, and so on. So we then, in the final result, dividing both sides by this big equation over here, we get that the value of this centroid for the x coordinate is 2.84 millimeters. So that is our answer, and we can box it. Next up, the sum of the moments about the x-axis is equal to the y coordinate of the centroid times the areas of each of these, the rectangle, the left triangle, and the right triangle. And this is in turn equal to the y coordinate of the centroid of the rectangle times the area of the rectangle, and so on and so forth. We then get a result of what the y value of the centroid being equal to 24.8 millimeters, and we can box that answer as follows. Thank you guys so much for watching this video, and stick with me for more videos regarding centroids and central mass.